Okay, in this video, we're going to use properties of logarithms and exponents to solve real-world problems. So first thing we need to talk about is orders of magnitude. And this is the number of multiples of 10 there are in one number compared to another number. For instance, Mercury is, and I have a typo in right here, but I will fix this in yours. Okay, Mercury is 57.9 billion meters from the sun, whereas Pluto is 5,900 billion meters from the sun. All right, so first let's look at those distances in scientific notation, because when you think about it, scientific notation is just the number showing us that multiple of 10. So it makes it a lot easier to compare them. So I have Mercury as 5.79, and then we need enough tens to move the decimal point so that we have that in billions. That would be 10. And then Pluto, that's going to be 5.9 times 10 to the 12th power. Okay, so if we want to compare them, Pluto's distance from the sun is how many orders of magnitude? Well, what we would do is we're just going to divide one into the other. So we're going to take the bigger one, which is Pluto, 5.9 times 10 to the power of 12, and then we're going to divide by, and what we're really looking at, or when comparing these, is we're just looking at, well, what's the difference here between these exponents? So Pluto's distance from the sun is 2 orders of magnitude greater than Mercury. Okay, I didn't put a line in here for this, but 2 orders would be 100 times further. And where am I getting that? Well, that is just coming from, move over there a little bit, 10 to the power of 2, right? So 2 orders of magnitude is 10 to the power of 2. So let's take a look at these examples here. Determine how many orders of magnitude the quantities differ. So we're talking about a kilometer and a meter. Well, hopefully you know that there are 1,000 meters to 1 kilometer. Now, maybe just looking at those two numbers, you've already figured out that it's 3 orders of magnitude. But if you're unsure, I can write my meters. My meters, let's write this, meters is the same as 1 times 10 to the 1, 2, 3. And then we're looking at our kilometers. Well, the kilometers is 1 times 10. Well, what can I put this 10 to the power of to keep this number as 1? Well, 10 to the power of 0. 10 to the power of 0 is 1. 1 times 1 is 1. So now when I look at the difference between these two, this is 3. So 3 orders of magnitude would be the answer for this one. Go ahead and try to figure out these other ones and then rejoin me when you're ready. Okay, $1 and a penny. So if we think about it, there's 100 pennies in $1. So you can just count up the zeros, or you can figure that in scientific notation, but we're looking at 2 orders of magnitude that they differ. Okay, a horse's weight, 400 kilograms, and a mouse weighing 40 kilograms. So how do these compare? Let's start by changing them to the same unit. So if I have 400 kilograms, let's just get them to kilograms. So if I have 40 grams, if I want to convert this, I would put grams at the bottom and kilograms at the top, and then it's going to make my units cancel out, so I'll be left with kilograms. So how many grams in a kilogram? Well, there is 1,000 to 1. So that means that when I go and figure this out, I'm doing 40 divided by 1,000. If I want to divide by 1,000, that just means I'm going to move that decimal point 3 places to the left. So 1, 2, 3. So 0.040 kilograms is our mouse. And then my horse is 400. Okay, so my horse, 400. I'm going to change this to scientific notation. Again, there's other ways of doing this. You might just see the difference in our decimal places. But when in doubt, this is a good strategy to use. So if I were to take 400 kilograms and change it to scientific notation, that would be 4 times 10 to the power of 2. If I were to take my mouse here, I'll do the mouse on the bottom in green, that's going to be 4, and I have to move the decimal place 2 spots to the right, so times 10 to the -2. Okay, and if you're unsure, if you need a little refresher on scientific notation, just come talk to me. So now I'm looking at the difference between the two. So 2 minus a -2 equals 4. So my answer here is that there are 4 orders of magnitude between the horse and the mouse. Okay, let's look at some different types of problems here. So the Richter scale. Okay, so here's the formula for the Richter scale, and you're probably going to want to pause the video, write down all these parts, and then rejoin me when you're ready so we can go over it. So hopefully you're familiar with the Richter scale in general. You've heard about it on the news. It's just how we measure earthquakes. So let's look at this, what each of these parts mean. So A is the amplitude in micrometers. So if we're talking about a wave here, you have to think back to trig. Whoops, that is a horrible wave. All right, our amplitude is how high it is. The period is how long it takes for it to repeat. So we have the amplitude in micrometers, and then t divided by t, the period of the seismic wave, so how long it takes to repeat, and then b just accounts for the weakening of the wave over distance. So as you measure further away from where the center of the earthquake is, it's going to get weaker, and so b is just a number that is used to account for this change in distance. Okay, so example, how many times more severe, I don't think that's spelled correctly, I'll fix that, was the 2001 earthquake in Gujarat, India, and then we're given our Richter scale number. Then the 1999 earthquake in Athens, Greece, again, we're given the Richter scale. So hint, you need to find the ratios of the severities. So we have how we're going to set this up. Okay, so here's the first part. We have the Richter magnitude, which is our R sub 1, and then that is equal to the log of the amplitude, the associated amplitude, over the associated period plus b, and all of that equals 7.9. So you can set the same thing up for R sub 2, and the R sub 1 here is just, we'll write India. Down here is Greece. So R sub 2 is just going to be log A sub 2 over t plus b equals 5.9. Okay, so we want to know the difference, right? We're seeing how many times more severe. So the way to do this is we're going to take our bigger one, which is India. So log all over t plus b, and subtract the smaller one, 2 over t plus b. And on the other side of the equation, we're going to subtract these as well. So we have 7.9 minus 5.9. Okay, first step here is just to distribute this negative. Rather than showing you what happens, I'm just going to, instead of writing this all out again, if this negative is on both the log and the b, we now have a negative b and a positive b. Well, those guys are just going to end up canceling out. So on our next step here, we have log divided by t minus log a sub 2 divided by t equals, and we can go ahead and subtract those as well, and we end up with 2. Now, when we're subtracting logs, to condense that, we're going to actually divide what's inside the log. So we have log a sub 1 over t divided by a sub 2 over t equals 2. When I divide fractions, I take the first one, I multiply by the reciprocal of the second one. That's going to make it so that our t's cancel out, and I will have log a sub 1 over a sub 2 equals 2. Well, we're getting closer because it said that we need to find this ratio. If you can find that ratio, then you can find out how much bigger it is, how many times bigger it is, and also the order of magnitude, the number of orders of magnitude. So this is log with a base 10. So I'm going to do 10. I'm just changing this to an exponential function. Okay, I have now isolated the part that it tells me to look for up here, and so 100. So it is 100 times bigger. The question was how many times more severe was the Indian earthquake than the earthquake in Greece? It was 100 times bigger. Didn't ask us for this, but just to be clear on the connection there, it is 2 orders of magnitude bigger. Okay, now hang in there because we got 2 more types of problems to deal with here. All right, chemical acidity. Let's get that formula in here. Okay, so we have pH equals the negative log of H plus. Okay, so what does this part right here mean? Well, this is the concentration of hydrogen ions in a solution in moles per liter. Okay, so let me explain how this works. You've probably heard about this in chemistry, but the lower the pH, the more acidic a solution is, right? And so you'll notice here that this is negative, right? So what that means then, is the lower the pH, the more acidic the solution is, but that means that there is higher hydrogen ion concentrate. Because as this number in here gets bigger, the pH is going to get smaller. So let's see how that works here. So some, especially sour vinegar, has a pH of 2.4, and a box of baking soda has a pH of 8.4. What are their hydrogen ion concentrations? So using the formula that we have above, we're going to be solving for this part. We're going to plug in the pH. So let's start with the vinegar. I'm just going to abbreviate here. So we have a pH of 2.4 equals the negative log of the hydrogen ion concentration. So to solve this equation here, I'm first going to divide by a -1, which gives me negative 2.4 equals log. Then that gives me a base of 10 to the negative 2.4 is going to give me my concentration. And so if I solve that, I'm going to put this in scientific notation, and we get 3.98 times 10 to the -3. All right, I want you to go ahead and try to figure out the hydrogen ion concentration for the baking soda. Once you got that, come back to the video and check your work. Okay, hopefully you started by setting up your equation like this. You divide by a negative, so you have negative 8.4 equals the log. Then we have base 10 to the power of negative 8.4 is going to give us our concentration. Plug that into your calculator and put that in scientific notation. We have 3.98 times 10 to the power of -9. Now, both of these are in moles per liter. Moles per liter. All right, our next question here. How many times greater is the hydrogen ion concentration of the vinegar than the baking soda? Well, we just have to compare our exponents here. And if we want to put them in scientific notation like we were doing earlier, if we want to divide them like we were doing earlier, then we'll see that we just need to subtract our exponents. And we need to put the larger one on the top and the smaller one on the bottom. So 3.98 times 10 to the power of -9. When I subtract those exponents, -3 minus a -9, I get 6. I also want to show you something over here. We could have even just gone back. If they hadn't asked us for the concentration, we have 2.4, right? So -2.4. 10 to the -8.4. If we were to just subtract these, we would have also come up with 6. 2 ways to think about the same type of problem. The question, however, is how many times greater? So when we're talking about times greater, that's not the same as order of magnitude. Quickly, let's skip down here. By how many orders of magnitude? Well, we figured that out. 6 orders. How many times greater? Well, we're going to go 10 to the power of 6. That means 1, 2, 3, 4, 5, 6. There's our answer for this part, and here is our answer for that part. All right, one more type of problem here. Newton's law of cooling. Okay, we got a lot of T's in here that mean different thing. So right here, this T, this is the temperature at a specific time. So temperature in terms of time. Because we see over here that we have time. So if we can plug in a time, we can find out the temperature in terms of time. Tm is the temperature of the surrounding medium. So what I mean by that is if you have something, it's absorbing the temperature of the stuff around it, right? So it could be the air around it or the liquid around it that is changing the temperature of the thing that we're talking about. T sub 0, hopefully you know that sub 0 always means initial, so initial temperature. We have the natural base. We have K, that's going to be some constant. And we have T, and that, of course, is time. All right, so let's give this formula a try with a problem. So a hard-boiled egg is at temperature 96 degrees Celsius and is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So we got to pull out what we've been given in this problem and figure out how we're going to attack the answer here. So a hard-boiled egg is at a temperature of 96 degrees. I'm going to say that is the initial temp. Right, because we're then transferring it into this cold water. So the cold water is then the temperature of the medium around the egg that makes it change its temperature. So we have 16 degrees Celsius. Well, that is, for colon, I'm collecting my information here. So that is T sub m. 4 minutes later. Well, that's time. The egg is 45 degrees Celsius. So what is that? 45 degrees Celsius. All right, so we have an initial temperature that we're starting with. We're submerging into water. Some time is passing. And then we have the new temperature of the egg. So if you look at here, what would that last part be? Try to come up with an answer in your head there. The last part is the temperature at a given time. So it's been sitting in that water for a little while. It's the temperature at the given time of 4 minutes. So what is it? It looks like we have all the pieces. What do we not have? Well, remember that E is a number, so it's not that we're solving for. For this one, we're going to solve for K. We need to find out what that constant is, so solve for K. Once we've solved for K and figured out the constant of when this egg changes temperature, then we can use that to determine how long it would take for it to get to 20 degrees Celsius. So let's go ahead and set up our equation. We should have 45 equals 16 plus our initial is 96 minus the temperature of the medium, which is 16, times e to the power of negative k times, well, we know the time, 4. Okay, so this is just an equation we need to solve. Again, remember that this is the part that we're solving for. Right there, we're trying to find out what k is. So we're going to work with our skills of solving exponential equations. First thing we need to do is isolate the exponential part. I can also simplify, actually, let's simplify this first. This part right here, parentheses, we can just go ahead and simplify that and make that 80. So I have 45 equals 16 plus 80. Then it might be more obvious what our exponential part is, but this is the exponential part right here that we need to get everything away from. So I'm going to subtract 16, and I get 29. Then I'm going to divide, well, actually, I'll just show you in different steps so we don't get lost in here. Then I'm going to divide by 80, so now I have 29 divided by 80 equals e to the power of negative 4 times k. So now here's the part that we need to solve this. Well, if I take the natural log of e to some power, that's going to get my some power down to where I can get to that x. So I'm going to take the natural log of both sides. Since it's an equation, I want to keep it even. And then I take the natural log. I'm showing you all the steps here. Well, these are just going to cancel out. I'm left with the natural log of 29 divided by 80 equals negative 4k. I'm going to divide by that negative 4. These cancel out over here. And what I want to put in my calculator is k. To find out what k is all of this. Okay, once you find out what that is, if you remember how to store a number in your calculator, store it as k, and it's going to make this next part a lot easier. Or at least a little more exact, right? Because we're not going to have to round off anything. So what we come up with is approximately 0.253, and there's some other digits in there. If you store it in your calculator, you won't lose any of those digits. So now that we have the k, let's go ahead and use that to find out how long it's going to take for it to become 20 degrees. So where does that 20 degrees go into our equation? Well, that is the temperature that the temperature after a certain amount of time. So we're going to put in 20 equals, the rest of our equation is going to look very similar, 16 plus, I already simplified this part earlier to 80, so I'm just going to plug in 80, e to the power of negative k, right, because I solved that, but that negative k is right there, times time. Now I can solve this equation for t. I'm going to subtract 16, then I'm going to divide by 80, and I end up with 4 over 80 equals e to the power of negative k times time. I'm going to take the natural log of both sides, which gives me this. Keep in mind this k is not a variable we're solving for anymore. We know what that number is. I'm leaving it as k in my formula here because I've stored it in my calculator. But I divide by negative k, and what I need to plug into my calculator, let me actually switch sides here so I can show the approximation on the other side. T equals the natural log of 4 divided by 80 all over, don't lose that negative k. Plug that into your calculator and you will come up with 11.81. Now, what did we find? All right, we got to the end of the problem. What did we actually find when we did all this? This is minutes. So after 11.81 minutes, our egg is 20 degrees Celsius. All right, that's it. That was a lot of information, a long video. It's just a lot of information to get to you, but hopefully these problems will go smoothly once you get started. All right, thanks for watching.